Hello. Today, we're excited to present our work called XINC. We seek to answer the key question, what does each neuron of an implicit neural network learn? And I'll explain a bit about how this works later. First, though, we need some preliminaries. Well, what is INR? Basically, it's a network that takes some coordinate input and gives some pixel output. And for the most basic INR, an MLP that takes XY coordinates and gives RGB pixels, we would just repeat this process for every single coordinate in the spatial grid. For a video INR, we could use an XYT formulation and then get pixels for every X, Y, and frame index, or we could have a convolution-based INR, which takes only the frame index T and gives us output the entire frame corresponding to T. And we would repeat this process for every frame in the video. We aim to explain the properties of INRs. And you can see examples on the left side for how we explain MLPs, and on the right side for how we explain nerves. And while I don't want to get too far into the details in this brief presentation, I will say that for MLPs, this involves taking the coordinate input, and for every single neuron or every group of weights in the feed-forward MLP, we will look at how it activates for every individual pixel, and we will store those results as contribution maps. For nerve, it's not as straightforward because we don't have XY input, we only have T input. So instead, we have to sort of work backwards. We need to account for the way kernels have their results combined into feature maps. So we essentially need to store the intermediate result to unroll those. And we also need to account for in the prior nerve blocks the pixel shuffle that happens, and we need to account for the fact that the pixels are upsampled layer after layer.
To demonstrate the utility of zinc, we use it to investigate the properties of INRs in 5 key ways. The first property we investigate is, what do neuron contributions correlate with? Here, we show contribution maps for a few neurons from each layer of the FFN network. There is a progression from representing Fourier features in early layers to representing more of the image with Fourier artifacts in the last layer. Meanwhile, nerve neurons tend to capture a variety of features, including edges, textures, colors, and depth. Thus, the behavior of a neuron in both networks is not simply to represent some pixels. Instead, it learns some low level scene attributes. In what ways do INRs represent information to include or omit concepts in a scene? In this figure, the top row shows the sum of all neuron contribution maps for the indicated layer. The second row shows the total raw image intensity. We also compute the difference between this total intensity and the total contribution to show when contribution does and does not correlate with intensity. The heat maps reveal a correspondence between the areas of large contributions and the areas of high intensity in the input image. However, these contributions are not dictated by raw pixel magnitude alone. The difference maps reveal that INR layers also pay attention to other low level information such as edges and textures. In the bottom image, we notice that neurons produce non-zero contributions even in regions where final output colors are near zero. Thus, NRs must represent to omit. Next, we examine the distributed nature of representations by investigating the number of neurons that are involved in the representation of each pixel. For this, we compute the density of neurons contributing above a certain threshold. The threshold for a layer is set using the xth percentile of sorted contributions of all neurons across image locations. We observe that high intensity and highly textured areas not only have high contributions as we saw earlier, but they also have a large portion of neurons dedicated to them. In particular, there is a large bias for edges with nerve. For FFN, the representation is more evenly distributed. In video INR such as nerve, motion drives contribution changes over time. We compute optical flow between two frames and the difference in total contribution maps between those same frames. Contributions to a given object remain fairly constant over time. Changes in contribution are focused more in areas around the regions of optical flow. When a moving object reveals new background, this causes fluctuation in spatially proximal pixels, even though they technically contain no motion themselves. Thus, we see that in spite of its lack of high level object semantics, the changes in how a nerve represents a video are dominated by the motion of entities. Finally, we can group neurons in terms of their contributions. We cluster pixels in a given frame according to Gabor filter features into K clusters and aggregate contributions to yield a K-dimensional vector representation for each neuron. This can be used to cluster neurons of each layer into 4 clusters, and we show 4 sample neurons from each cluster. Note how neurons belonging to the same cluster tend to learn similar contribution maps as opposed to neurons belonging to different clusters. For more details, we encourage you to visit this QR code.